Okay, now I got to figure out how to unshare it. Okay, I guess you guys are back with me. Were y'all able to see that all right?
Yeah.
Okay, I've never shared the application before, so one of my UC students taught me how to do that. What was that? Have you seen that Newton's Cradle before? You guys seen that before? Probably seen that.
Yes.
So that's kind of neat because it demonstrates something. Basically, it's a mechanical equivalent of something electrical that I want to talk about today. So let me explain something that was going on here, and then I want to relate it to electrical engineering. I want you to imagine that you have something like Newton's Cradle. Let's say I have a rod, and I have two metal balls just hanging from the rod. One like this, and one like this. And what I want to do, let's say this is, call this ball A and ball B. So I got A and B. And what I want to do is I want to take ball A and I want to pull it up like this. And when I do that, I have to do work to pull it up. And the work that I do is now stored as potential energy. When I let it go, ball A will hit ball B. Now what I want to do is I want to transfer the energy that I'm giving it. I want to transfer the potential energy to kinetic energy. And then the kinetic energy ball A has, I wanted to give that kinetic energy to ball B. Would this work, this scenario, would that work? If I want to give, if I pull this back and give ball A potential energy, I let it go, so now it has kinetic energy. It's going to strike ball B. And I want ball A to give the ball B all of the energy that it has, all the kinetic energy. Can I transfer the energy that way? Well, would this scenario work? If yes, tell me why you think it'll work. If no, why won't it work? Can I get ball A to transfer all of its energy to ball B the way you see it on the board? If I pull ball A back and let it go, what's going to happen when I let it go?
It's going to hit ball B.
It's going to hit ball B, and then what?
It's going to give energy. I don't know if it will give all of the energy.
I think you guys kind of do know, though. I mean, just from experience, ball A is a lot less massive than ball B.
Yeah.
So it doesn't make sense that when I pull ball A back, it's going to strike ball B, and since ball B is so much more massive, ball A is going to give some of its energy to ball. Excuse me. Ball A is going to give some of its energy to ball B, so ball B will move over a little bit, but ball B has so much mass compared to ball A, and ball A is going to hit ball B. They'll both move over a little bit, and then ball A will go bouncing off back the other direction. Does that make sense? Can you kind of see that from the picture?
Yes.
Okay, let's reverse this. Let's reverse it. Let's say this is ball A. This is ball B. I'm going to do the same exact experiment again. I'm going to pull ball A back, give it energy, potential energy. I'm going to let it go, so now it has kinetic, and then it's going to strike ball B. What's going to happen?
Ball B might fly off the rod.
Yeah. Now ball A is so much more massive than ball B. Ball A is going to hit ball B and give it some energy. But the fact that ball A and ball B are going to continue up, right? They're going to continue up, which means that ball A didn't give all of its energy to ball B. I mean, just think about it. If ball A gives all of its energy to ball B, what should happen to ball A?
It would be stationary.
It would be stationary. It would stop. If ball A gave all its energy to ball B, then when I move this up, ball A would hit ball B and stop because it doesn't have any energy. It gave all its energy to ball B, and then ball B would fly off with the energy that ball A had. You see what I'm saying? How can I make that happen? How can I make ball A hit ball B and stop, and then ball B fly away with the energy that ball A had? What needs to happen? What do I need to do?
Make them the same size.
Make them the same size or make them the same mass. If both have the same mass, but make them exactly the same, they don't look the same. If I make, well, you know what I'm trying to do. If I make them the same mass, now when I do this, pull ball A back, give it potential energy, let it go, it now has kinetic. Ball A will hit ball B, ball A will stop, and ball B will fly off with the energy that ball A had. You saw that. That's why I showed you Newton's cradle. Now, it moved a little bit because, I mean, in the perfect world, there wouldn't be any movement at all. You saw that when in the video, he picked up one ball, it hit one ball on the other side went up. If you picked up two balls, it hit two balls on the other side. Whatever energy he gave the left side, the right side responded in kind. And so what had to happen is the mass of one ball had to equal the mass of the second ball for all the energy to be transferred from one to the other. Well, mass in this circuit is like resistance. Mass in this circuit is the mechanical equivalent of resistance. Matter of fact, they use mass or inertia to represent electrical circuits in a mechanical way. So mass is the opposition to motion. The more mass something is, the harder it is to move. Resistance is the opposition to current flow. And so this is the circuit. You might recognize this because last time we were together, we talked about something called Thevenin's theorem, the Thevenin equivalent circuit. And I showed you how to take a circuit and go through some steps to come up with this circuit. So if you go back, you look at the video, this is kind of where we left off. We Thevenized the circuit and we ended up with a Thevenin voltage of 6 volts and a Thevenin resistance of 2 ohms. Now, the Thevenin circuit is the circuit from the point of view of what? What did we say?
The load.
The Thevenin circuit is the circuit from the point of view of the load. Whatever you hook up to the circuit, if you have an amplifier and you hook up speakers to it, the Thevenin circuit would be what the speaker sees. If you have a cell phone charger and your load is your cell phone, the Thevenin circuit would be what the cell phone sees when you plug it in. Whatever the load is, the Thevenin circuit is the circuit from the point of view of the load. So we Thevenized the circuit the other day, and we came up with this, RTH of 2 ohms and a Thevenin voltage of 6 volts. So now, what does that mean? Well, it means that this load resistor doesn't know anything about the original circuit. We had a 9-volt battery, we had a 3 ohm resistor, a 6 ohm resistor in parallel. But this load doesn't know anything about that. This load only sees 6 volts of voltage, 2 ohms of resistance. That's what it thinks it's hooked up to. And now what I want to do is talk about power. I want to talk about something called maximum power transfer. So let me go back and share the document with you that I had posted and you copied notes on. I think you copied notes on it, but it was this one. And this was our list of theorems. And if you look closely at number 2, you will see a statement for maximum power transfer theorem. Let me read this to you. Maximum power transfer theorem: a load will receive maximum power from a linear bilateral DC network when its total resistive value is exactly equal to the Thevenin resistance of the network as seen by the load. Let me read that again. Maximum power transfer theorem: a load will receive maximum power from a linear bilateral DC network when its total resistive value is exactly equal to the Thevenin resistance of the network as seen by the load. In other words, if I want maximum power, if I want maximum energy to go from ball A to ball B, the only way to make that happen is the mass of these two have to equal each other. And over here, if I want maximum power to be transferred from the voltage source to the load, the only way that can happen is the resistive parts of this has to equal each other. If I want maximum power transfer to happen, then the value of the load resistance must equal the value of the Thevenin resistance as seen by the load. So if I want maximum power to come from here to here, then this resistor value has to be 2 ohms. It's got to match that, like these two masses have to match. Listen, I'm not saying that we have to make this 2 ohms. I'm not saying that. This could be whatever value you want it to be. What I am saying that if your goal is to have maximum power transfer from this battery to here, the only way that's going to happen is if these match. If you don't care about maximum power transfer, then they don't have to match. But if you want maximum power to go from whatever this device is to over here, these two got to match. Now, I asked in the last class, nobody spoke up, if any of you guys were in the audio. Back in the day, we used to hook up speakers and amplifiers and radios and cars and all of that. And I didn't really understand what I was doing because I hadn't took my degree in electronics or physics yet. I didn't know. I was just hooking stuff up. I learned as I went. But one of the things I noticed when I hook up amplifiers, here's an amplifier. And an amplifier has a left and right channel. We got a left channel and a right channel. An amplifier has a left and right channel because when we hear, as humans, we hear in stereo. We have 2 ears. And so when we reproduce music, we want to hear it like we hear it as a human experience. So we have two ears. We got a left and a right ear. We got 2 channels. And so I noticed when I was hooking this stuff up that the connection points with the speakers, it was a 4 ohm there. And on the right channel, the connection point for the speakers, there was a 4 ohm there. And what that meant was, well, I thought what it meant was you need to hook up 4 ohm speakers. And you do. You would go out and you would get speakers. And you can get speakers of any ohmic value you want. But I would get 4 ohm speakers and hook them up to the amplifier. Let's say this is a 100-watt amplifier. I would get 4 ohm speakers and hook it up to the amplifier because there was a 4 there. And I thought the 4 was saying, hey, you need to hook up 4 ohm speakers. That's not what it meant. This 4, if you think about it, the input of the amplifier is over here. The speaker is the load. What this 4 means is looking back into the output. The Thevenin resistance of that amplifier is what? 4. If I drew an equivalent circuit, here it is. I would draw the Thevenin equivalent circuit. The inside of the amplifier has a total resistance of 4, as seen by the speaker, as seen by the load. I'm going to draw a DC source because this is DC, but the amplifier is really AC, or a combination of DC and AC. So I got my power source there, VTH, and the internal resistance as seen by the load is 4. And so I can hook up whatever speaker I want. If I want to hook up a 32 ohm speaker, I can do it. It'll work. If I want to hook up a 100 ohm speaker, I can do it. It'll work. But if I want all of my 100 watts to go from the amplifier to the load, guess what? Then the resistance of this has to equal the resistance of what I hook up. This is a very important thing, guys, especially if you go on in electronics and you take communication electronics, and this comes up in so many places. So when I was taught Thevenin's theorem, the professor told me that this is really important because we can greatly simplify a circuit. We rather work with the simple circuit than with the more complex circuit, since they're both equivalent. I think I mentioned that last class. But in my mind, to me, is this. Maximum power transfer allows you to see what ohmic value does the load need to be if I want to get maximum power transfer from the source to the load. And you can only see that when you Thevenize a circuit. So maximum power transfer happens when the value of the load resistance matches the value of the Thevenin resistance as seen by the load. Now, normally there's an exercise I send to you guys and have you go through it to prove that. I give you a Thevenin circuit and I give you 3 resistors, one that matches the Thevenin resistance and 2 that don't, and actually calculate power. And then you can see, you can prove to yourself that, yeah, I calculate maximum power when RTH and RL are equal. I usually do that when we're face to face, but since we've been on video, I haven't done that. So I don't know, I'll think about doing that. I do owe you a quiz though. I told you I was gonna post a quiz for you, so look for that. I haven't forgotten about it, I just haven't gotten around to it yet. So, maximum power transfer, this is pretty much it right here. This is it. The words sound complicated, but look how simple this is. If I want maximum power transferred from the voltage source to the load, then the value of the load resistance has to equal the Thevenin resistance as seen by the load. So that's what I want you to do. I gave you a list of steps to properly Thevenize a circuit. Take that list out and you'll need a sheet of paper, actually several sheets of paper. I'm going to share a document with you with some practice problems on it to Thevenize. What I want you to do here is do the first problem. Now it's important, very important, I don't know how far we'll get today, but it's very important that you understand each and every problem because each problem is designed to teach you something. And when we get to that thing that is designed to teach you, I'm going to say, all right, here's what this circuit is about. You got to understand that concept or you're going to have trouble later on in the course when we use this. So take out those steps that we went over in the last class, the steps to properly Thevenizing a circuit. Look at the very first circuit on the sheet. Draw the very first circuit on the sheet. Then I have all these quantities over here that I want you to solve for right here. I want you to find RTH, I want you to find BTH, I want you to find the input resistance, I want you to find the output resistance. Draw the Thevenin circuit and determine the value of load resistance that will allow maximum power to be transferred from the voltage source to the load. See what you can do with the first one, figure 1. I'll give you a few minutes to do it, and then we'll look at it together. All right, guys, I'll give you 1 more minute. I'm going to talk about the problem. 1 minute. All right, let's take a look at this problem. We'll go through it step by step. And then if you didn't get this one correct, you'll have another shot at the next problem. Did anybody get a value for RTH? How much is the Thevenin resistance?
Is it 3 ohms?
3 ohms. What about VTH?
8 volts.
8 volts. All right, well, let's see. So, step 1, what is step 1? What do I do first?
Remove the load.
Remove the load. Raise it. Step 2 is what?
Name your terminals.
Name the terminals. Now, probably not. Well, maybe Monday or Wednesday, you'll see why this step is important. I'm going to give you a circuit that if you don't name the terminals, you won't be able to keep track of them. So I'm going to call this terminal A, terminal B. That's the next step. Name the terminals. What's the next step?
Find voltage across the load.
Find the voltage where the load used to be. So the load was between terminals A and B. So if you take your voltmeter and hook up between where the load used to be, it's called the open terminal voltage. You want to ask yourself, what resistor am I across? And whatever resistor you're across, if you find the voltage drop across that resistor, that's your value for VTH. If I connect between terminal A and B, which resistor am I across? Am I across R1 or am I across R2?
R2.
Or 2?
I'm directly across R2. I'm not across R1. This one is across R1, but this one, the battery's there. So I'm across R2. If you find the voltage drop across R2, and you found the voltage from A to B, if you find the voltage from A to B, and you found VTH. Let's do it. I'm going to show you 2 ways, but after this way, I'm only going to use voltage divider rule. The Ohm's law way, from the point of view of the voltage source, I have a series circuit. Right? So I got to figure out, all right, how much current is in this series circuit? Well, all series circuits are solved the same way. First thing you do is you find the total resistance. That total resistance is 16 ohms. Now that total resistance is also called the input resistance. One of the things I asked you to find on this problem is the input resistance. The input resistance, the total resistance, or the equivalent resistance for parallel, they all mean the same thing. In textbooks, they'll call this the total resistance or equivalent resistance. In the real world, you'll never ever hear that. You'll hear input resistance of this device or the input resistance of that device. So 16 ohms is my input resistance, my total. Next, to solve the series circuit, once you find the resistance, find the current by taking the total voltage, dividing it by the total resistance from the step above. So I got 32 volts. I got 16 ohms. It gives me 2 amps. So in this loop right here, I have 2 amps of current flowing. I like to put a square around my ammeters so they stick out. I usually use a circle for voltmeters. So then the last and final step is I can figure out the voltage from A to B. Voltage from A to B is going to be the current through the resistor that's connected between A and B times the value of that resistor. I get 8 volts. 8 volts. Another way I could have did this, that thing is much cleaner, much better, is the voltage divider rule. Voltage divider rule says if you want to find the voltage across a resistor, take the resistor, if you want to know the voltage across, divide it by the total resistance, and multiply that fraction by the total voltage. And that'll give you the voltage that you want to know. So I could have said, instead of doing all of this stuff, I could have said, all right, my voltage divider rule, I want to know the voltage across the 4 ohm resistor. Put that in the numerator. That's like that R. Divide that by the total resistance. Well, my total resistance, that's the resistance that the battery sees. You said that was 16 ohms. Take that fraction, multiply that by total voltage. Well, the total voltage is 32 volts. And that'll give me the voltage I want to know. 16 to the 32 is 2. 2 times 4 is 8 volts. I never have to find current doing this. I save a step, and on the exam, that could help out. Save a step. Either way, you got it. 8 volts is the voltage that load thinks it's hooked to, and 3 ohms of resistance is the amount of resistance that the load sees. The load doesn't know anything about a 32-volt battery. The load doesn't know anything about a 4 ohm resistor. The load knows nothing about a 12 ohm resistor. This is the circuit the load sees. Now they say, all right, well, if I'm going to actually hook up a load to this circuit, I'm going to hook a load up, and then I tell you, I say, all right, Mr. Engineer, electrical engineer, I want this load to receive maximum power. What size should I make this resistor? What ohmic value should I make this resistor if that resistor is to receive maximum power? How many ohms should that resistor be?
3 ohms.
3 ohms. This resistor sees 3. If I want maximum power to go from this 32 volt battery, to that load, that speaker, that light bulb, whatever this device is, if it's going to receive maximum power, the only way it's going to get it is I got to make this resistor match that one. I got to make this 3 ohms. So on the quiz, remember that. Actually, the quiz one is not too bad, but on the exam, there's a question on exam 2 that deals with Thevenin's theorem and maximum power transfer. And students miss it all the time. It seems like a simple concept, but you got to really think about this circuit. I'll have more to say about that later. So I don't know how many of you actually got this, but I'm going to give you another circuit here, and I want you to have a second shot at trying to get the correct answer. Whoever said 8 volts and 3 ohms, you were dead on it. Exactly right. Good work. But if you didn't get it, try again with problem number figure 2. Now, remember I said it was a takeaway? There's a couple takeaways from this sheet. There's some things I want you to learn. Well, here's one of the problems where you have a takeaway. So go through, see what you can do, and there's a very, very important lesson that this circuit is designed to teach you, and I'm going to talk about that after you had a chance to work it. So go ahead and see what you can do with this problem. Okay, guys, one more minute, and then I want to have a look at this problem in 1 minute. Okay, I want to give you a little bit more time, but in the interest of time, we have to go over it now. Let me ask you a question. What is the input resistance of this circuit? How much resistance does the voltage source see?
6.
Okay, somebody says 6. Anybody else?
I got
Now this is RN, not RTH. Looking this way. Looking that way, there's your eyeball. How much resistance does this see? Somebody says 6. Somebody else have a different answer.
I second the 6.
Okay, let's check it out. Now, if you want to find the input resistance of the device, remember the load is not part of the device. If I say find the resistance, the input resistance of your cell phone, you wouldn't leave your cell phone hooked up to it. This load is like your cell phone. If I want the resistance of just of the circuit, just the device, you got to remove the load. So I want the resistance just of this part right here. I got to take away the load. And then you say, all right, if I take away the load, what path does current have? Which resistors does current flow through? Whichever resistor, this is how the battery feels what's out there by sending current out. So if there's a resistor that no current goes through, as far as the battery is concerned, it's not in the circuit. So if you just trace current around as it leaves the battery, current comes up here, it feels 3 ohms of opposition from R1. It gets to this point, it has no reason to go through R3 because it's an open circuit. So no current flows through R3. Therefore, from the point of view of the voltage source, it ain't there. Current flows through R1 and R2. It fills 6 ohms of resistance. So the total resistance, the equivalent resistance, the input resistance of the circuit, 6. Now let's Thevenize it. So Thevenize it. We remove the load. Well, we've already done that. Step 2, we mark the terminals. We call one terminal A and terminal B. Step 3, if I put a voltmeter between these 2 terminals, which resistor am I across?
R2.
I'm across R2. If I hook up a voltmeter between terminals A and B, I'm across R2. Now, I know what some of you are thinking. You say, hold on a second. Singleton and whoever that was that said R2. What about R3? If I connect a meter up, since R3 is connected to point A, terminal A, how can I just ignore R3? How much is the voltage drop across R3 and why? Why do you answer the way you do? What's the voltage drop across R3?
50 volts.
Across R3?
Oh wait, no. It would
How
be
many
0.
volts? 0. This resistor right here drops absolutely no voltage. And the resistor does not drop in any voltage, basically it's a piece of wire. What do you mean it's not dropping any voltage? Why you say that? Well, in order for a resistor to drop voltage, it's got to have two things. Number one, it's got to have a resistance. Well, we got that. But it also has to have a current flowing through it to get the voltage drop. Well, we don't have that. Since this is an open circuit between A and B, no current flows through R3. If you have a 1,000 ohm resistor, now listen to what I'm saying. If you have a 1,000 ohm resistor, any resistor, you have any resistor laying on the table, how much resistance does that resistor have? The answer is 0. I don't care what value it is. A resistor with no current going through it cannot resist. There's nothing to resist. And as counterintuitive as it sounds, a resistor laying on the table is exactly like a piece of wire. Because in order to have a voltage across it, it's got to have a current flowing through it. And so if I don't have a current flowing through a resistor, if you see a resistor just hanging there, the other side is open, no current flowing through it, you might as well replace it with a piece of wire. You can do this if you wanted to. That resistor acts just like a piece of wire. And if that resistor acts just like a piece of wire, then if I connect between A and B, I'm connecting across R2. So that's the takeaway. That's the thing I wanted you to learn about this circuit. When you see a resistor just hanging there with no current going through it, and that happens anytime the other side is not connected, then that resistor is acting like a piece of wire. So if I want to figure out the voltage from A to B, it's going to be the voltage drop across R2. And since R1 and R2 have exactly the same value, each one of these is going to get half the voltage. R1 is going to drop 50 volts. R2 is going to drop 50 volts. Therefore, the voltage from A to B is going to be 50. Therefore, VTH for this circuit is going to be 50 volts. Make sure you understand why. Any questions over that? I'm gonna do this to you now. I showed you this the other day. Remember we talked about open circuits and short circuits? And I gave you a series circuit like this. And I think we had like 3 resistors or something in here like this. And I put these points up here like this. Point A, point B, point C, point D. And let's say that this is 30 volts. And all these resistors have the same value. Well, if this is 30 volts and I have 3 resistors of the same value, then every time current passes through a resistor, it's going to create a voltage drop of 10 volts, 10 volts, 10 volts. Each resistor is going to drop 10 volts. Now, if I come over here and I open this up, the current stops, like turn off a switch. So the current stops. It takes a current passing through a resistor to make the 10 volts. If there's no current, can't generate a voltage drop. All these voltage drops drop to 0. If you measure from here to here, you're measuring 30 volts. Same exact concept. Very important concept, but one that often students mess up for some reason. So you see it? Does that make sense? I can't see if you guys are saying yes or no, and I got my dedicated, John, where'd your dog go? Wouldn't your dog just stand there?
Yeah, there's something that grabbed her attention outside.
I was kind of like, his dog was just like chilling, just laying on the couch, thinking, man, that dog is like chilling, boy. And then I turn around, he's gone. Is it a he or she? She's gone. My dog does exactly the same thing.
I think she was reading off of my barometer because I was like, of course, I got a call from the attorney when you were explaining that. So,
it's a good thing that's on video.
I said a couple choice words and she got up and left. So,
well, that's a good thing about the video. So this is some good stuff, guys. This is one of my favorite topics to talk about because it has so many applications. And I I know a lot of you, especially the older guys, you got to go and get your associate's degree and start making money. You got families. But some of you younger guys, I hope you think about taking a double major or getting a 4-year degree and doing some of this advanced stuff. I mean, you're young enough. You got time to do this stuff. This is some really, really cool stuff. And you're really living in an exciting time with all this technology and nanotechnology, all this stuff going on. It's a really, really exciting time to be alive. So BTH is 50. And again, we'll do more of this on Monday. But make sure you go back and replay this video and try to understand why it's 50 if you missed something. We got to find RTH. So what I'm going to do now is put R3 back in the circuit. And to find RTH, what do? Well, I got to set the power source to 0. If I have a current source, I open it up to make it go to 0. If I have a voltage source, I short it out to make it go to 0. Well, I got a voltage source there. So I'm going to replace this voltage source with a short circuit. Now I'll just draw this little wire right here to represent a short. And I'm going to come over here on the output, and I'm going to look in there to see the ohmic values and how they connect to each other. Now, I want somebody to tell me in terms of, my erase this. Tell me in terms of R1, R2, and R3. I don't want the value, the numerical value. I want to know what's in series with what and what's in parallel with what, looking in this way in the circuit. Tell me what to write. R1, R2, R3. Tell me how they're connected.
R1 and R2 parallel, R3 in series with R2.
Exactly. Now, I don't know if you guys follow what he said. He said R1 and R2 are in parallel. How does he know that? Because he can see that this side and this side are connected together. And this, once I put this short here, it connects the other two sides together. So I have two side-by-side resistors connected, they're in parallel. So he said that R1 is in parallel with R2, and the parallel combination of those two resistors is in series with R3. Put those values in there, and you get RTH. So make sure you study this when you go back and rewatch the video and understand how we get this from that. And of course, I can switch these around. I can say R3 plus R1 parallel R2. The order doesn't matter. But anyway, I have R1 and R3. I got 3 ohms for R1 in parallel with 3 ohms for R2 plus 1.5 for R3. And then if I have 2 resistors, equal resistors in parallel, I can just cut them in half. So this would be 1.5 plus that 1.5. If I add those up, I get 3 ohms for RTH. So my Thevenin equivalent circuit has an RTH of 3 ohms. I guess I kind of did the steps out of order. No, we didn't. We already solved for BTH because these two were equal, right? We didn't have to do any calculations for that. If they're equal and they're in series, they get half the voltage. So that's why I thought we did this already. This BTH was 50 volts. Now, if I go back to my original circuit, and I want to connect the load up to this. Maybe the load is a speaker, might be a light bulb, might be, I don't know, it might be a resistor, it might be, whatever the thing is that you're feeding, whatever this is designed to power, whatever the load is, I'm going to represent it as a resistor. And that resistor, RL, is allowed to be any ohmic value in the universe, any value you want, as long as you don't care about power. If you care about power, you say to me, I want maximum power to go from the battery over here to that load. There's only one value for which that will happen. What value do I need to make RL if I want to receive maximum power transfer from that voltage source to that load device? How much does that have to be?
3 ohms.
3 ohms. 3 ohms. Even on the exam, if you get it wrong, let's say you get the wrong RTH. Let's say on the exam it's 3, but let's say you wrote 5. When I ask you what size does the resistor need to be, if I want maximum power to be transferred from the voltage source to the load, if you give me the wrong answer, you still got credit for it, full credit. If you say, even though it's supposed to be 3, if you come over here and you say, all right, that needs to be 5 for maximum power, as long as I see that these two values match, you got 10 points on the exam. Gotta know maximum power transfer theorem, and then you're good to go. Guys, I apologize. I have an appointment at 2 o'clock. I'm already late for it. So normally I hang around and ask questions. I got to run right now, but if anybody has any questions, please send me a text. I've been really kind of being pulled all kind of different ways between my mom, a project I'm working on in school, but things are finally kind of coming to a close for me. So send me a text, and it may not be until tomorrow when I can respond. But I will respond to it, I promise you. And if we need to meet or whatever, we can do that. Questions?
I already sent you. This is John. I already sent you a text.
Yeah, I saw your text, John, and I thought I responded to it, but I don't think I did.
No.
So I'll respond to your text, John.
Okay. All right. Appreciate it.
You guys okay? Tim, Riley, everybody, people are signing out, so I guess you're good. So guys, please watch the video, and I'll respond to some of these texts and emails tomorrow, and then we'll get through it. We'll do more of this on Monday. Have a great weekend, and I will see you later.
See you.
Have a good one.